You see, in the last few classes, we are discussing about the simplest representative of multi-degree of freedom system, which is two-degree of freedom system, and which will basically provide you the conceptual background about the multi-degree of freedom system. Because in multi-degree, no, just only the size will increase, but the conceptual things will remain same. And then in the uh, while going through the last part, what we realize that we are getting coupled differential equations. That means both the degrees of freedoms are being present, and that's why we were not in a position to directly solve the differential equation, because for a simultaneous equation it is possible that if you have that many number of equation which is equal to the number of variables, then you can solve it. But in differential equation, it's altogether a different ball game. I mean, even if you have say two number of equations and two number of variables, but if the equations are coupled, then you can't solve it. I mean, that is the whole problem, and that's why we try to convert this into eigenvalue problem, and we got an infinitely many solutions. And later on, we will see that how we can use this concept for solving the more generalized situation where in a two degree of freedom system the forces are acting in both the directions, or in a multi degree of freedom system the forces are acting along more than one degrees of freedom, and then how this force vibration, coupled force vibration equation we are trying to solve. Now we'll try to see that the coupling is arising due to a different reason. In the first case, whatever we have discussed, the coupling is occurring because of the fact that both the masses carrying both the degrees of freedom, they are connected by springs. So it is because of this common connection this whole thing is occurring. Now here we would see that because of the coordinate system there may be coupling. Because of the choice of the coordinate system, the coupling may get introduced. So look at the rigid bar, which is supported by two springs K1 and K2 at the two ends, and these springs are hinged with the bar so that the bar can freely rotate. Now, can you tell me that if we apply some force at any generalized point, say somewhere here, then what will be the deformation of the system? Will it be only undergo translation, or will it be only undergo rotation, or it will undergo both under translation and rotation? Can anybody suggest? Anywhere a force is being applied, then it is trying to create a deformation in this spring. Now, because of the deformation, spring will exert some upward forces as is being shown here. Okay. Now, if it so happens that if the resultant of these upward forces passes through the same line of action of the force which is acting downward, the applied force which is acting downward, then what will happen that there will be no couple and there will be only translation. And somewhere we will call the center of stiffness. That means if the line of the resistance force exerted by spring and these two springs I can try to find out that what the points through the resultants are acting, you know that we can simply apply the kind of formula that mm, that x equal to, if the distance is x from the left hand side, then k1 x1 plus k2 x2 divided by k1 plus k2. All of you know that how to find out the line of action of a set of parallel forces. So I mean line of action of the resultant of a set of parallel forces. So if these two lines coincides, the downward force and the upward reaction, then it will purely undergo translation, because then there is only uniform deformation in the two springs, though the stiffness is different, but the deformation will be same, and then the spring will undergo a translation. But if it doesn't happen so, that K1, K2 are having such a value that whenever the deformation is trying to take place, then the forces which are being generated, the upward forces which are being exerted by these springs, the resultant of them passes through a point which is or resultant is having a line of action which is different to the downward force applied. Then what will happen that in order to the translation, I mean apart from the translation, then a couple will be formed by these two forces, and that will try to create a rotation. So it will undergo rotation. So in a generalized form, we have tried to show this figure. We have tried to draw the free body, that some downward forces is acting here, and then because of that, it is not necessarily at the point which is the through which the resultant of these two forces in the spring passes. Therefore, so this downward force is acting here, and the acceleration, because of the acceleration we have considered downward positive, deflection we have considered downward positive. So for the acceleration, the D'Alembert's force is mx double dot. Therefore, now it is becoming so, after introducing the D'Alembert force, we can consider that the system is in static equilibrium. And then if I take the two equilibrium equation, one is summation of the forces at zero and another is summation of the moments at zero, then we will basically arrive at these two equations. Is this understandable to everybody? What about others? That means what we are writing here is that mx double dot, actually if I write the static equilibrium equation, we would have got mx double dot upward, this also upward, our downward direction is positive, so everything is negative. That means minus mx double dot minus this term equal to 0. So that we are writing in a form mx double dot equal to, I mean mx double dot we are taking on the left hand side, and we are getting the right hand side this equation. Is it understandable? Then we'll get one more equation for the rotation, because when this will undergo a lateral movement, it will also, that is also undergoing a lateral a rotational movement phi. So there will be a rotational acceleration too, and that rotational acceleration in the same way. That means if we apply the D'Alembert's principle, if we apply a just to convert into equivalent static system, if we apply a moment opposite to the direction of rotational acceleration, and then if we consider the rotational equilibrium, then just in the same way we will get this j, where j is the polar moment of inertia. That means if I have an axis vertical to the screen of this laptop, so About that, the moment of inertia, if it rotates, the moment of inertia, whatever we'll get, that normally we call, that is actually the summation of the moment of inertia about the two horizontal axes, and that we denote by J, which is called as the polar moment of inertia. So J phi double dot equal to this expression. So just we are taking the after applying all the after applying the D'Alembert's forces and moments, we are converting the system into equivalent static system, and then we are taking the moment. Or even somebody could have taken the could have considered it through Newton's law, that well, these are the upward forces and this is the downward acceleration. Therefore, the total unbalanced force is equal to mass times the acceleration. Similarly, the total unbalanced rotation, sorry, total unbalanced rotation with rotational acceleration phi double dot, that is equal to j phi double dot into the unbalanced moment which is being applied here. Is it understandable to each other? Then we have to think how we can try to solve it. You see, we just if we rearrange it, if we just wanna have this x double dot as coefficient 1, so we have to divide by m both sides. Similarly, on the for the second equation, if we wanna have the phi double dot as one coefficient, so the second equation comes like this. That means our objective is that we wanna have a mass matrix as unit matrix. So if both the equations, if we try to write down in the matrix form, then we will get it like this. Okay, that the unit matrix into the vector containing x double dot and phi double dot, that means the acceleration vector, plus stiffness matrix. This all this should not be 1, it should be L. So what we are getting sorry, is like this. Again, see, here will be a suffix 1. So now you see that the this equation we cannot solve because we are having this coupling term. That means in the first equation only x double dot is present. Then when it is being multiplied here, x is present. But then when it is multiplied by phi, then this term is creating all the problem. That means it is introducing coupling. Similarly, for the second equation, this term is creating problem, and this is introducing coupling. So that means because of the choice of the particular coordinate system, the coupling terms are coming. Because if we would have chosen the coordinate system in such a way, this L1 and L2, I mean the coordinate system, if we would have chosen in such a way that K2L2 minus K1, that means K2L2 would have been equal to K1L1, then what would have happened, that here we would have got 0. Is this understandable? So this is called the static coupling. This is occurring because of the stiffness term. That means if somebody would have no acceleration condition, x double dot and phi double dot equal to 0. That means even if we were interested in the situation that we have applied a static force, And then under that force, if we are interested to find out how much is the translation and rotation, then what would have happened that this part would have gone out, only this part would have been there, and here some forces and moments would have been there in this null vector. Now, then also these coupling terms would have been there, and then we could have, of course, solved the simultaneous equation. But if they would have been zero, then we could have directly solved the equations very simply. And if they would have been non-zero, then we would have to solve it for the way we solve for simultaneous equations. So that means this kind of a coupling is occurring for the static activity, because the stiffness acts even statically. But if a system doesn't have acceleration, then really there is no inertia force acts, and there is no dynamic activity in the system. Even if a system doesn't have acceleration but it has uniform velocity, then also we will not consider that it's a dynamic system. It's a as per Newton's law, you know that if a body is given an initial velocity v in the space, then for the infinite time, and if there is no other disturbance or perturbation to the system, then that body will keep moving for infinite time, maintaining the same velocity. So it is as good as a kind of a static condition. The condition is not changing. So here the coupling we are getting, that is for the static issue. That means it is a stiffness related coupling. And then if we just consider another situation where, I mean a most general situation, where we apply the force, say somewhere here, which is other than the centroid point. So in that case, there will be D'Alembert, say at point C, which is a general point and which is at a distance of E from the centroid. So there will be, then our coordinate system is having the origin at this particular point. And then, so in terms of that, if we try to write down the equation, then you are seeing that these will be the two forces, and the D'Alembert's force will also be there here. So because of this shifting of the coordinate system, what will happen that the acceleration of this point will be different from the acceleration of this point, and it should be h double dot c plus e into phi double dot, because the rotational acceleration is also causing or also making some contribution in the movement. Am I able to make you understand? Hello? Say if I get a rotation here, phi, then if I am interested in calculating the deflection here at point C, then the deflection, or deflection will be then xc plus e into phi. So the acceleration will be the double derivative of the same, x double dot c plus e into phi double dot, isn't it? So in the same way, if we write down the equations, then what will happen? So in the moment of inertia, we know that we get mass into then the distance by which it is being shifted, that extra terms, and then so that will be added with the moment of inertia about the centroid, and then we will get the right hand side like this, just in the same way. And then if we just try to write down the equation, then Uh, if we consider K1L1 equal to K2L4, then what will happen that this will vanish, but this mass matrix will have the off diagonal terms. So we can call now the coupling is occurring for the dynamic activity, and so it is called dynamic coupling. And there can be, is it digestible to everybody? It is not the general situation. Actually, there should be terms involving from this K1 and K2. So these terms, but particularly you see here, like we considered if K2 equal to L2, the K2 L2 equal to K1 L1, then these coupling terms will become zero. Similarly, there we are getting it in such a way that if K1L1 equal to K2L2, so then sorry, L4, then it should be 0, and then this should be L3. So so this coupling is due to the shifting of the coordinate system by a distance e. And that occurs because the inertia force changes. Okay, so this is called dynamic coupling. And then if we go to some other point where this is not satisfied, then we get a generalized situation in a simplified form where we will have both mass matrix having the coupling, and also the stiffness matrix is having the coupling. That means both are having off diagonal terms, and we can say that this kind of a differential equation is having both static and dynamic coupling, and that is the most generalized situation. Okay, so in a most general situation, we would like to have we will have this kind of a form. Is it okay? So, is there any question, whatever we have discussed so far?